I am going to, over the next half hour, introduce you to the concept of Ohm's law, one of the fundamental principles of electronics and electricity. An understanding of Ohm's law is essential to any further study of electronics or electricity. This is the formula for Ohm's law, and I'm going to go into greater detail as we go along. Some of the terms we're going to go over the next half hour: resistance, how a conductor interferes with or resists the flow of electricity through that conductor; voltage, current, and power. Power meaning essentially work. Before we delve into Ohm's law, what I'd like to do is discuss with you just a little bit of some fundamental algebra. Dust off a few cobwebs if you haven't done any formula manipulation anytime recently. And a very simple formula: A times B equals C. Or in the case of, we want to find the area of this rectangle. So we look at the length times the width, A times B, and the area is C. We can manipulate this equation any number of ways in order to find an unknown quantity. If we know the area and we know the length, we can manipulate the equation to find out what the width might be. Conversely, if we know the width and we know the area, we can manipulate the equation and determine what the length might be. Those are some of the examples down here, and this type of manipulation is what we will need to do with Ohm's law as well. So it's really nothing more complicated than this. So don't let the math scare you. Ohm's law was discovered, if you will, by a German physicist and mathematician named George Simon Ohm. He lived in the late 1700s, early 1800s. As a result of his discoveries, the unit of resistance is named in his honor, and the symbol is the Greek letter omega, which we say Ohm, which is not the same as chanting or meditating. Mr. Ohm essentially stated that the current through a conductor between any 2 points, between the beginning and the end, for that matter, is directly proportional to the potential difference, or what we now call the voltage, represented by the symbol E, current by the symbol I, as measured across those 2 points. Further, we discussed that the current through the conductor is inversely proportional to the resistance, R, or what we have already looked at as being called ohms. Again, this is the formula: I, the current, equals E, the voltage, divided by R, the resistance. Now, how does that relate to what Mr. Ohm stated? The current I is directly proportional to the voltage. I equals E. Forget about the R for right now. So it's directly proportional. And it is inversely proportional to the resistance. If, again, you kind of forget about the E for a minute, I equals something over R, or 1 over R, or the inverse of R. All right, so that's where the inverse portion of that equation or description comes from. Let's use a simple example. I have a 60-watt residential light bulb, and residential voltage is typically 120 volts if you were to measure it at a receptacle. So I did that earlier. I measured the voltage in a receptacle and determined that it was in fact 120 volts. And the light bulb that I have here in my hand is 60 watts. So over here I have a device that I can use, a lamp holder, to demonstrate this concept. So I'm going to measure the resistance of this light bulb while it's cold. There is a significant factor here, that's why I mentioned cold versus hot or warm, as we'll see later. And I'm measuring 19.7, let's say 20 ohms. Well, then I'm going to insert this light bulb into the lamp holder. And this is not something that you should do at home unless you're very familiar with your test equipment and can safely wire an object like this, because 120 volts is very, very hazardous. use of the wrong test equipment and the wrong application can also be hazardous. So again, this is not something that you would typically do at home. So I'm going to plug this in, and the light bulb is giving off light. Essentially, the resistance of the filament is causing it to glow. Now I have here an ammeter that I can measure the current flowing through this conductor, and I get 0.5 amperes. And we haven't learned what an ampere is yet, but we're going to here shortly. And if you can see here on the display, it says 0.5 amperes. And earlier we came up with approximately 20 ohms of resistance. So from Ohm's law, I know I have 120 volts, and I now know that I have a half an ampere of resistance. So I should be able to calculate, half an ampere of current. I should be able to calculate the resistance. As you will see on the next slide, though, it really doesn't work that way. There are some variations in the calibration of the instruments and so forth that cause some error, but not as much as we're going to see here. Earlier, when it was a little bit warmer in the room, I measured the resistance of the lamp as approximately 17 ohms. We had 20. If I have a current of 5 amperes and I put those two variables, remember I have two knowns, one unknown, I put that in Ohm's law, and I would come up with a current of approximately 7 amperes, or 14 times what I measured with my meter. Where does that error come from? Well, unfortunately, the resistance of that element is influenced considerably by temperature. So as that bulb heats up, the resistance increases until it stabilizes at the resistance that results in the measured current of 5 amperes. Now we really can't measure the resistance of that light bulb when it's operating, especially at 120 volts. What we can do is, since I've let that light bulb operate here for a minute or two while I've continued talking, I can very quickly unplug the light bulb, set up my meter again to measure the resistance, and see if I can get a much closer number, just so that it looks more realistic. So I'm going to unplug the light bulb, and I'm going to very quickly fasten my leads to the terminals here. Well, I'm actually only getting about 23, and now it's back down to 20, so the light bulb cooled off very quickly. So, unfortunately, here in the lab, I'm not able to demonstrate the concept to you quite as accurately as I would like. However, we can continue on understanding these issues. As part of Ohm's law and the different ways you can manipulate the equation, I'm now going to introduce something that I call the pie chart. P-I-E. We know I is current, we know E is voltage. What is P? Well, we're going to find out here in a minute. It's power. This is an example of the pie chart that can be found on the internet, any number of locations. You simply do a web search or Ohm's law pie chart, Ohm's law chart. You could come up with something like this. And the nice thing about this chart or wheel is that if you want to find out what the resistance might be, you can define the equation rather readily depending on which two knowns you have. So if R is your unknown, you have E and I as your knowns, then this is the formula. You don't have to derive it every time. After you use it over and over again, as a professional might do, then these formulas become pretty easy to recall. But even then, I refer to these charts quite often to make sure I haven't gotten confused. We don't need to worry a whole lot about the rest of the formulas, but this chart does include the concept of power, which is a variation that we can get from Ohm's law. We're going to go into it here in just a minute. So over the last little bit, we've discussed current I, voltage E, resistance R, and then I had used the term watts when I was discussing the power or the intensity of the light given off by that light bulb, 60 watts. Where does that come from? What are watts? Well, Mr. Watt was essentially a contemporary of Mr. Ohm. They were in the same general time frame, overlapped a little bit here or there. Mr. Watt was a Scottish inventor and a mechanical engineer, early 1700s to early 1800s. And as a result of his endeavors, the unit of power has been named in his honor, which is where we get the watt. And of course, you're all used to paying your power bill and hearing about kilowatts and That's how the power company bills you for the energy, the power that you consume, the electrical energy that you put to work. Mr. Watt's primary effort or claim to fame was that he improved the steam engine, which prior to his efforts had been incredibly inefficient. But his improvements made the steam engine incredibly efficient, and as a result, had a major influence on the Industrial Revolution, not just in Great Britain, England, that area there, but the rest of the world. He further developed the concept of horsepower as determining the amount of work that an engine could perform. And we've all heard of horsepower when we've seen car ads, and when we buy a car, how much horsepower does the engine have? How fast will it go? How quickly will it get there? And that came from Mr. Watt. And over time, we've learned that 1 horsepower equals 746 watts. So if you have a 1 horsepower motor, it's pretty safe to determine that the motor will consume 746 watts in terms of performing 1 hour of work. The relationship between Ohm's law and power, we have determined through experimentation and other methods over time that power equals current times voltage. Now, you can put this into Ohm's law and substitute I or R or other quantities, and you'll get one of these other equations. This equation itself is extremely important to the electrical power generation industry, because this is one of the reasons that they generate electricity at such tremendously high voltage, tens and hundreds of thousands of volts, because it turns out that the resistance of the wire causes a tremendous amount of what's called voltage drop, and the voltage drop is a function of the square of the current. Well, if watts is the amount of power being generated, it actually becomes a constant. So if we can raise the voltage really, really high, then we can drop the current really, really low. And as a result, you have a very low amount of current being carried over this wire at a very, very high voltage. And the square of a very small number is still a pretty small number. So your losses in transmission are incredibly low. So the power company loves that. But if we go back to the light bulb that we experimented with just a few minutes ago, we know that it's 120 volts and the light bulb is rated 60 watts. Well, let's see how this can confirm or deny some of the measurements we took earlier, since the calculation showed the bulb actually should be consuming 7 amperes, but it was only consuming half an ampere or 500 milliamperes. Again, we go back into these equations. 60 watts equals the current times 120 volts. We can manipulate that equation to where watts divided by volts will give us the current. And 60 divided by 120 gives us a half an ampere, 500 milliamperes. That's what we measured. So obviously our measurement of the resistance of that filament cannot be accurately made, because as the calculation showed earlier, the resistance of the filament when it's operating at full operating temperature should be somewhere around 240 ohms, not 20 ohms. But you can certainly go through those equations yourself. Just to close, a little bit more history. We learned just a bit about George Ohm and his contribution to electricity and electronics through the discovery of Ohm's law. A little bit about James Watt and power. There's 2 other terms that we've used continually throughout this presentation that are related to other forebears. First of all, potential difference. The symbol is E from electromotive force, and the unit is volts. We also call that voltage. Think of that as the pressure behind the electricity that's flowing through the pipe. Current flows. Voltage is a potential difference or a pressure created between 2 points. It's named after Alessandro Giuseppe Antonio Anastasio Volta. One heck of a name, but he's an Italian physicist and chemist. He invented the chemical battery. And so that was a tremendous contribution to all of our efforts. And he lived again in the same general time period as Mr. Ohm and Mr. Watts. And then we have current, or I, with the unit of amperes, named after André Marie Ampère, a French physicist and mathematician, who was considered the founder of classical electromagnetism. and electrodynamics, or essentially how motors work. If it wasn't for electromagnetics and electrodynamics, motors could not turn. So that was his contribution was incredibly valuable in terms of how we obtain work today with the electricity generated from the power companies delivered to our homes to power the motors that compress the refrigerant in our air conditioning systems, that turn the fans that blow the cool air into our house, and so forth. So that has been a brief introduction to the concept of Ohm's law, fundamental principles of electricity that will then go further into electronics. As you continue on with the course, you'll delve more and more into Ohm's law as it applies to direct current circuits, which is basically what we've used here as our examples, although the light bulb is alternating current. Another factor in the discrepancies we have in the resistance of the light bulb is with alternating current, we actually run into some characteristics of impedance, which incorporates the resistance of the wire along with what's called the inductance and the capacitance of the wire, other characteristics that are only really of impact when we have alternating current. But that's way down the road. You really need to get well-founded in the fundamentals with Ohm's law before we get deeper into a lot of these other subjects. Thank you.